Okay, so this is the second video on module theory. In the last video, I just introduced you to what is a module and what topics I am planning to cover in the next 8 to 10 days. So, as I said, in the first part, things will be mostly familiar and mostly related to what you know, and mostly will be like the what is the module, submodule, question module, what's module homomorphism, the free module, that's it. So those things will be mostly similar to what the concept of vector space is. So firstly, let me define what's a module. Uh, so you have a commutative ring with identity one, and aim is an R module, or I should say left R module, or similarly right you can define if uh, firstly M plus is an abelian group, and secondly there exists a map from R cross M to M such that R times say A plus B goes to R dot A plus R dot B. R1 plus R2 acting on A will be same as R1 acting on A plus R2 acting on A. This addition is the module addition and this addition is the ring addition. That should be clear from the context. And R1 R2 acting on E is same as R1 acting on R2 acting on A. The associativity. These two are the distributive properties. And the last one is one acting on any A. Okay, so this is exactly the vector space structure. So vector space in particular, if you ask me for example, if V is a vector space and V is also F module. If V is a vector space over the field, yeah. So this is exactly the same thing. And similar to vector space, you can define the submodule, quotient module. I'll come to it. So firstly, let me give some more examples. So firstly, R is, and because this left means the ring element is acting on the elements of M from the left. So similarly, you can define a right module. And in general, I will just talk about a module without being specific whether it is right or left. You can assume it to be left module always. That will not cause any problem. So firstly, R is the module over itself. You can always define R is the module over itself. But R is just a commutative ring with identity. That is easy. Number two, any abelian group is a Z mode. And the action is again clear. If you take any integer n and if you act it on any group element R is coming from say an abelian group G, the addition notation. So in R is just R times R plus R n times, provided n is positive. If it is zero, then it is of course zero. So one not that. If it is negative, we're just adding minus R. That is the additive inverse of R. So this will make R as Z module. Just for trivial examples. Uh, Also, you can take this R-fold Cartesian product and you can make it an R module with the usual component-wise addition and the scalar multiplication, as you know, in the case of vector space. And also, mm, say, I can define this. Suppose V is a vector space over A. V over A is a vector space. Okay. And we have a linear map T from V to itself. So now I can define V as an fx module. And you know what I'm doing. Like if you take any polynomial fx and act it on V, this will just land to this will just go to ft acting on V, where ft means you are taking x to the t. So This is just the map, and one, or I should say, the constant term, you are taking it to the identity of it, right? So A0 will go to A0 times identity for any A0. So in particular, if fx is summation ai x power I from 0 to k, it will act on v, and this maps to summation ai t power I acting on v, where I is from 0 to k. Yeah. So these are some examples. You can uh, give more examples, like actually you can construct more modules. Like we have V as a module over it, and I constructed a module over a different ring fx, the polynomial ring on one variable over the field A. Okay. Now you can construct even more modules. So for example, let me take this one. Uh, say let me take, suppose M is given to be an R module. M over R is a module. Okay. And you have I and ideal. These things are given to you. Then uh, you need to assume one thing to make this an R mod I module. So module over R mod I. What is this thing? That should be clear to you once I define this. So what is this operation? You take any such R plus I acting it on M. And this is just clear. This is this. Where this dot is the module operation of R over M. And to make it well defined, what you need? You need for R1, the image of R1 and R2 is same, then you need to have R1 minus R2 belongs to I, and you need m times R1 minus R2 should go to 0, because that will give you R1 in same as R2, right? Or I should, let me, otherwise it should be confusing. Uh, right. So for that you need I to be inside what is called the annihilator of M. And this is defined to be all those say elements of R that annihilates every element of it. This is again, you can see this is an ideal. So because if this holds, then because this is in this also belongs to annihilator of M in R. And again, so by definition of annihilator, this is here, this is same. This defines an R module or R mod I module. I should say. You can make M to be an R mod I module, given that M is an R module. Okay. And now, say, suppose you have, say, a ring. Okay, suppose A is a ring, and you have a homomorphism from R to A, where R was just any commutative ring having identity. And moreover, you have a ring and you have this homomorphism, ring homomorphism. Okay. Then you can make A as R module. And the most obvious way to do, say, if you take any R from R, A from it, you just map it to this. And remember, f of R will land inside A, so this is just the ring operation of A. So you can again check that by property of homomorphism and etc. The A will be an R module. Okay, so enough of examples. Now, say, so similar to module, suppose you have another subgroup of M, which, like if you restrict those scalar multiplication, external scalar multiplication operation to that submodule, if this again the map is well defined, then that is called a submodule, right? So the definition is same as subring or subspace in vector space. We will say if n is a subgroup of M and for all R belongs to R and xy belongs to n, if this belongs to n, then say n is a submodule of n. Okay. The usual definition of subspace. This is just similar. And whenever you have a submodule, you can talk about the quotient module, right? This quotient group you can take and you can make it a module. Say the elements are obvious, this type of cosets, the collection of distinct cosets of n inside M, and you can define it as an R module by means of this, right? And you can check this easily. This is a well-defined map because easy. If M1 plus n is same as M2 plus n, then M1 minus M2 belongs to n. And because n itself is say submodule, any r dot this will again land inside n. So by those distributive property and all, this minus this belongs to n. So the class of this is same as class of this. That is again easy. So all these things are similar to what we have already seen in vector spaces. Yeah. So I'm not going into details again because those things will just be a repetition. Uh, Now, so we have the notion of quotient module, submodule. So let me just quickly again define what's the module homomorphism. All these things you see are everything similar to the notion of vector space. So again, module homomorphism will correspond to a linear transformation. So what you do, you have two R modules, M and N. You have a map such that phi of any say Rm plus n is R of Pm plus Pn for all m belongs to for all m belongs to m, for all n belongs to n, for all r belongs to r. This is a module homomorphism. Again, that's easy. Now you can even take this collection of all module homomorphism. Say you have two modules, right? M and n. So over R. So you can consider all such module homomorphism. And the question is whether this again defines a R module. Like R can act on this the usual. If you take any R and say if you take any F, this will just map to this function or this homomorphism, which is just if you take any. So R dot F is a map from M to N. So if you take any small m, this will be R dots F of M. Remember, f of m is inside n. So, and n is an R module. So, this dot is coming from that R module property. So, you can check this also. I think will be this makes home set is again an R module, and in particular, this home of m comma n is denoted by the endomorphism of m. This is just really easy thing to see, and so again, if you have a bijective homomorphism, then that's called a module isomorphism, and you have these uh, isomorphism theorems, just like you have in group theory or vector space or ring theory. So isomorphism theorems. The first one is, of course, you know, if you have this, then this quotient module M over kernel of P is isomorphic to the image of. Well, the kernel is all those elements of it that maps to 0 under phi, and image of phi means all those phi of x where x belongs to it. So I'm not writing them. This is the first isomorphism. Second is again if you have two submodules, um, suppose say A and B are two submodules of say M, then just like vector space, you have this is isomorphic to this, but the plus means exactly same as vector space, the all possible sum. And you can check this again defines a module or a submodule of M. And the third one again, if you have B contained in A contained in M, then what should be this? This M mod A by B mod A is isomorphic to M mod. Or wait, let me just think. So A is bigger than B, so I think we need to switch it. So, yes. So you have M, so A is smaller than B, B is and then yeah, then it's fine. So these are the three isomorphism theorem, and you have that correspondence theorem that gives you a bijective correspondence between submodules of this quotient module with submodules of M that contains M, containing say M. Where what is this map? This is just the usual one. Like if you take any submodule, say n prime, which is bigger than n, then just map it to n prime mod n. Just this. And yeah, you can show this is an bijective, like you can show this is an injection, surjection. Sometimes this is called the lattice correspondence. Okay, so these are all those things that you are familiar with. Mostly all of them are similar towards the vector space. So yeah, now I can talk about the next natural thing that comes along with vector space, the basis, the concept of basis. So here, so firstly, you need to know what do you mean by a generating set in a module. In a vector space, a set generates a subspace. Means all elements of that subspace is a finite linear combination of elements of that set that you have started. So here again, the definition is somewhat similar. So firstly, so let me define. So this topic is under free mode. Okay. So so first, let me start with the generating set. The generating set is suppose you have just a set A. So you have A just a set input, not any submodule or sub. Okay. And so the or let me just make it so you have M given to be an R module and you have a subset of A of M. So we can take this that is all possible R dot A where R belongs to R, A belongs to A. This is a finite set. So you can easily see this again is like is, this is a submodule. That is easy to check. This is a submodule of M. In fact, it is the smallest submodule containing A. Of course, the set A is here because you can take the one belongs to us. You can in particular take in A dot one. This is A and it belongs to us. Ra. So this is called the submodule of M generated by the set A. Okay. And if the set is finite, then you say this is the finitely generated submodule. And by smallest I mean if you have any other submodule, so this smallest should be clear. So if N is a submodule of M such that N contains A, then N should contain R, right? And that is again clear because if A is subset of N, then any R dot A, because A belongs to N and N is a submodule, second belongs to N. And because N plus is again a group, so all possible finite sum will again belongs to N. So in particular, if you take all such elements, this will give you this module R. So R is subset or submodule of N. Yeah. So that is by the definition of R elements. So now if there exists such a set A such that RA is M, then we say M is generated by A. And if A is finite, then M is finitely generated model. Finitely generated model. Yeah. And if A is singleton, say single element is, then we say M is a cyclic model. Just like a cyclic group. M is a cyclic model generated by the element X. Okay. So this is about generating set in a module. This is exactly similar to a vector space, right? So now the second thing what we need to give definition of a basis, you need the independence. A subset, this is again a subset, set inclusion. The normal is linearly independent if whenever you have any finite linear combination where Ri belongs to R is 0, then you have each of the coefficient is 0. This means the set A is linearly independent. And if M is generated by such a linearly independent set, then we say M is a free module. Free module generated by A. This is similar to the concept of basis, right? So in particular, if M is this Rn, where R is the ring on which the module is, like R is a base ring. So then you have A as this vector, right? Where the ith component is 1, otherwise all components are 0. So yeah, this is just an example of free module. For example, Z is uh, free module generated by 1, and this N is called the rank of module. Oh, sorry, I mean N means the cardinality of the basis. So this is similar to the dimension. So this is if it is finite, then it makes sense, right? Otherwise, rank does not make sense. So if cardinality of it is just rank of M. Yeah. And now here you can take like there is the universal property, which is again really obvious once we see. So suppose you have just a set again. I'm saying just to emphasize, you have a subset A of M. Then there exists Or I think we don't need to take any set. Just let me start with any arbitrary set. That will be much easier. So let me just say let A be any set. Okay, just a non-empty set. So then given any set map, okay, because A is no structure, so we need to talk about only set map. We cannot be talking about homomorphism, etc. So given any set map phi from A to some module A, there exists a free module if A such that there exists unique psi from FA to M such that so you have phi from A to M and naturally you have this inclusion map, right? Because FA is the free module generated by A. So you have already the copy of A is inside FA. So you can talk about this inclusion map such that this diagram commutes. So you have A inside FA and you have a map from just a set map from this phi. You have this inclusion map. So it then lifts to this psi. So that this diagram is commutative. So this means psi composed with the inclusion map is phi. Okay, so firstly, we need to define such a free module. Okay, so let's see. And A is any set. It's like it's not saying A is a finite set or not. If A is empty, then you can take the free module to be zero. Then there is nothing to show because if the set is empty, then there does not exist any phi at all, right? Or you can say there is just only trivial map from this, like from the empty set to any module. So what should be this free module? Firstly, we need to mm, give like you have to find a set such that it has a module structure, and not only that, it has a basis, and the basis should correspond to A. So I am claiming this map from say you can take any say you can take all possible function from A to R. R was just a ring we have. The R module M is over R. Yes, any map. Okay. So you can define, you can take this set and you can just talk about this of any A. So you can define the sum of two maps, like point wise usual. And if you take any R and from A, so this will define R of F. Right? If A is in R and R is a ring, so this multiplication is on the right side is happening inside R. Okay. So yeah, so this defines F is a module. And of course, you have this copy of, or I should say, yeah. So the copy of A is inside it, right? Because you can always talk about these constant maps. So the copy of A is inside FA, and then you can just given any phi, you can define the map psi from FA to M. So you have this map phi to from A to M. So you need to define this. So what you do, remember this is a free module generated by the elements of A. So just take in Ri Fi, then this will just map to summation Ri. So this is just a map from say A to R, right? And then this should map to an element of M. And remember where each Fi is just a set map from A to R. So you can take let's say let's see what we can do. So we have any element is of this form, then yes, So you can define fi of say a, right? You can define this. Or let me just see it again. So you have this set, and this defines a module via this. This is a module over R again. Okay. And then you have this phi map. Oh, we need to use the map phi, yeah. So because you have phi, you need to match these relation or this commutative diagram. You need to also take care of this relation. So then you can just, because phi is a map from A to M. So just this should not be uh, okay. Let me just make it here too. So just take any this, and because it is generated by E, so you can take this where AI is coming from E, and then just take phi of phi acting on the AI. Right? And so then you can easily see if you have A belongs to FA, where A is from A, so then what will phi A do or psi A do? This will get mapped is to phi A, right? So you get this inclusion is exactly equal to phi. Yeah. Okay. So this is the universal property of a free module. Yeah. Now, okay. So this is what I plan to talk in this video. So this is a free module, and you can take this exercise. This you can find. This is not really easy to show, but this is not really difficult. Actually, just need some points that is, I think that is there in the book of Damit and Food. I don't remember the page. Maybe it's some exercise of page three. I think 368 or 360 or 350. I don't remember. So it says that it is free module, but you cannot say any like product of like any arbitrary product of free module is free. So what does it say? It says that if you take this, that is product of Z is not. So there are these three, four steps mentioned there, so you can follow them and I think you can do. I don't remember the page. Maybe it's from it's between 358 to 360. It's an exercise thing. That's I know. Okay. And so let me just come because I defined the product. So let me just define what's the direct product and direct sum. So let's just define it. So let me define what's the sum of modules. So if you have N1 up to NRB modules, R modules, then their sum is just all possible in this. This is you can see it's the module. This is the sum of module. And you have this direct product of modules, or so say product of module, not direct. That N1 cross to NR. This is just all these R tuples. Again, that's easy to see. We're using component-wise addition and component-wise scalar multiplication of each ni. You need to use the fact that each ni is an R module. So to show that this product is R module, right? And you have this three equivalent relation, which is I think same for vector spaces also. So let me just define it as a proposition. What it say? What does it say? It says that suppose of the following are equivalent. So the firstly consider this map from N1 cross N2 cross N to this sum. You can already guess what the map is. You can take N and just map it to the sum. Um, My handwriting is getting terrible. Yeah. So this, uh, wait a second. Yeah, sorry. So yeah, this is an isomorphism. And second is if you take any G and if you just intersect with this where I is running from into R except J is the zero vector for all J between 1 to 1. And third, any X in this N1 plus N2 is a unique, uh, or I should say, yeah, has a unique representation. Sorry, this has a unique representation as sum of elements of this unit. This representation is unique. So to show all of them are equivalent. So let's just show it very quickly. So firstly, let's see what. mm Firstly, 3 to 1 is the easiest because what does 3 say? It says that firstly it's easy to say that this the map pi is a homomorphism. That's really easy to see. Homomorphism is a module homomorphism. Yeah. So that you can just easily show using the for component wise product like any R acting on this component under this map pi will go to just R dot N1 plus up to R dot N1. Oh, sorry, the R are both R subgroups. So let me just take in E. So this will just go to A dot N1, but again it can come out and this again will be pi of N1 up to N. So you can easily show that this is a ring homomorphism. And from 3 you get any x from this codomain has a unique representation. So it shows that the map is surjective as well as injective because there cannot be more than one representation. So phi is iso. From so 3 to a is easy. Let's just see. So 3 to 1 is easy. So from say 1 to 2, what you can do. So let's see. So suppose you have any element xj in this intersection. We need to show xj is 0. Okay, so by definition of sum of modules, you get xj is sum of xi from 1 to r except j. Right? You get this, and then so what you get? You get x1 plus up to xj minus 1 plus minus xj plus again xj plus 1 and up to x r. That is 0. But because pi was an isomorphism, So this tuple, which minus x sub of pi is 0, but because pi is isomorphism, the kernel is only 0. So this means the vector itself is 0. In particular, the z coordinate is 0. So minus xj is 0. So you get xj is 0. Yeah. So it shows 1 implies 2. Now from 2 implies 3, uh, say, oh, that's again very easy because suppose you have x as 2 representations. Say summation of ni and summation of ni prime. Then take any ng. So, or maybe I should take, so let's just take this right hand side to left hand side and subtract it. Yeah. So I can write it in this way, I from 1 to r. Uh, okay. Then let's just take any j fix. Okay, just fix any j between 1 and r and keep that nj minus nj prime in this side and the rest on the other side. That is just ni prime minus ni I from 1 to r, I not equal to j, but this belongs to, on one hand, this belongs to nj, so this belongs to nj, and from this side, it belongs to the intersection of sum of ni, where I is not equal to j. So by 2, this is the 0, so you get nj is same as nj prime, and this holds for any j. So you get that x as a unique representation. Oh, so this was all that I was planning to say in this video. So you should be interest. And I've already shown three, right? All of them are really trivial to show. You just follow from the definition and whatever the assumption that you were starting with. Okay. So these are all the boring part actually. This is just exactly same as the vector spaces. But yeah, that is the one exercise that may be like something non-trivial. So you can see the hints were there in the book of dummies. Okay. So from the next video, I will start with the somewhat interesting part. So I will begin with what are, let me just briefly outline it. So I sorry, I was just a bit quick in this video because I did not want to take more than one video to finish it. So maybe the video is already a bit too long. So I'm sorry for that. But I really did not want to take more than one video to finish all this usual stuff. Okay, so for the next video onward, I will talk about, say, just briefly outline. So from the next video onward, I will start with the notion of exact sequences. I will take this home functor, these two, and I will show how left exactness is preserved, or I should say these are left exact. And maybe I will also talk about what are functors and categories, and to show that one of them is contravariant, one of them is covariant functor, covariant, contravariant. And then maybe I will take two or three separate videos to make to discuss snake lemma for two videos because it's just a bit too long for one video and five. So for that we need this exact sequence. So maybe after finishing this exact sequence part in the next 1 or 2 videos, I will talk about the snake lemma and five lemma, and then maybe we can go to homology theory, or then I can talk about tensor products as well. So if you just end this video here. So